All right, let's go back to that example of a spanning set that felt a little bit different than some of the other ones. The 1, 0, 2, 3, 0, 1 set. So we knew this spanned R2, but it felt different than the other sets that spanned R2 because somehow that 2, 3 we didn't need. And you may have picked up on why this is or seen different ways to think about it. One way is to say that 2, 3 we didn't need as one of our building blocks because we could already build it. And so that's what I'm writing down right here. So 2, 3 was somehow redundant for us because we didn't need to be able to build, because we didn't need it to build things, we could already build it. So we can make it out of the other two. Okay. And so there was no sense in keeping it in our set of building blocks because we knew how to build it with just the two. Now, this can get a little bit tricky because I could also say, like we could say that 0, 1 is redundant because I can write 0, 1 as this linear combination of 1, 0 and 2, 3. So let's see if we can fill in those blanks. So if I want to write 0, 1 as this linear combination of these two things, it looks like I need a third here so that I can get that 1 set. And then I have a 2/3 in the first component, and so I better get rid of a 2/3 here. And so that will work. And then I could do the same thing and say 1, 0 is redundant. Look, I can build it out of the other two. So there's sort of a weirdness here that means it's hard to just define what we mean by this being too big by talking about redundancies, because we could call any of them redundant. And so we'll come back to that in a minute. But let's look at one more example. So let's think about our Q adjoin root 2, root 3. So we had a spanning set. We had 1, root 2, root 3, root 6, but how did we know that we to stop there? So what if I thought about root 6 times root 3 and I wanted to put root 18 in there? So you may already be yelling and saying, oh, root 18, but that's root 9 times 2, which is just 3 root 2. And so root 18 is redundant. It's 3 times one of our building blocks already, right? So root 18 is redundant, and we don't need it. On the other hand, we could use it just fine and get rid of root 2 if we wanted to. So again, there's this complication of how do we know which one we want to get rid of? And I'm going to show you this next definition that helps around that sort of complication. So this is a definition for linearly independent vectors. So a set of vectors, and again, I lost my squiggly brackets there. So a set of vectors is called linearly independent if the only way to solve this equation, this linear combination equal to 0, is by making all of the scalars 0. So that's called the trivial solution. Okay, so linearly independent means the only way to make 0 is with all 0 coefficients. All right, why is this related to what was going on up here? So the reason why is because these equations that I wrote down where we were showing what was redundant, they could all be rearranged to look like that. So I could make this say 2 times 1, 0, plus 3 times 0, minus 1 times 2, 3 is 0, 0. Okay, and this one, same deal. I could rearrange this to be minus 2/3 times 1, 0, plus 1/3 times 2, 3, minus 0, 1 is 0, 0. So just by subtracting to the other side, I can write all of these equations as setting some expression equal to 0, 0, some linear combination of the three vectors equal to 0, 0. And if you look at those two things in green that I did, they're actually the same equation, right? If we multiply this bottom one, the one at the bottom of the screen, by -3, I think, then what we get is the top one. So these really are the same equation, and they're both showing you how to get 0 in a not trivial way, in a way that's different from just all 0 coefficients. And notice our second example here was the same. So our root 18 equals 3 root 2. We can easily rearrange that to say 3 root 2 minus 1 root 18 is 0. And so again, we're able to write 0 in some way that is not just 0 coefficients. So instead of talking about these redundancies, instead of saying I can already build that vector, what we do is we show that we can build 0 out of the vectors that we have in a way that's not just using none of our building blocks. Okay, so it's linearly independent. The only way to make 0 is with all 0 coefficients. And then we call it linearly dependent if we can make 0 out of a non-zero linear combination of the vectors. Let me fix that. All right, so if we can do that, if we can make 0 out of a non-zero linear combination of the vectors, then what we're saying is that it's redundant, and that there are some redundant vectors in there. And this lets us, instead of having to decide which one is going to be the one that's redundant, we get to just set up this equation with 0 and see if we can find a solution for it. All right, so let's look at some examples. So the set 1, let's see, what's the one that we've used? I don't remember if this is exactly the one I had before, but let's do it. 1, 2, and 2, 3, I think is the one that we've been using in examples. This is a linearly independent set of vectors. And in order to show why, what we do is we set up, could I make A times 1, 2 plus B times 2, 3 into 0, 0? So what are the solutions to this? So I'm going to multiply through my A. So I'll have A, comma 2A plus B, comma 3B equal to 0, 0. And if I add those vectors and equate the components, I have an A plus 2B as my first component equals 0. And I have a 2A and a 3B equal to 0. And now I'm in a position where I have a linear system of two equations. And I'm going to solve for A and B. And I'm going to leave that for you. You should try this solution. What you'll get is that A is 0 and B is 0. So you should work that through and try it, but that's what should happen out of doing this. All right, so here's another linearly independent set. So the set 1 root 2 is linearly independent. And so we're in this setting of thinking about Q root 2 as a Q vector space. All right, and then 1, 2 is linearly independent. Why? If we have A times 1 plus B root 2, and that is 0, this was actually a homework problem that you did. If a plus b root 2 is 0, you showed the only solution was if a is 0 and b is 0. Okay? And so what we were doing there with why do we care if something is 0 is really getting at this idea of linear independence. Okay? So another one, the set 1, root 2, root 3, root 6 is linearly independent. Okay, and here we're taught q root 2 root 3 as a q vector space. All right, so that set 1, root 2, root 3, root 6 is linearly independent. Why? Again, this should feel familiar because only way to make a times 1 plus b root 2 plus c root 3 plus d root 6 equal to 0 is if a equals b equals c equals d equals 0. And so we've already laid the groundwork to show that these sets are linearly independent. All right, so next time around, we're going to put these two ideas together, spanning and linear independence, and see what that gets us.